Assalamu alaikum and greetings. Text of this task is determine inductivity between toroid with N1 loops of conductor and coil 2 with N2 loops of conductor. So we have one toroid with N1 loops with the current I, and we also have a second coil with N2 loops, and we need to determine inductivity between these two. And we know that the inductivity of the first conductor on second, or second conductor on the first, is the same and can be calculated, for example, as a flux which first conductor creates on the second conductor divided with its own current. In our case, that is current I. So, in order to calculate a magnetic flux, what will we do? Well, firstly, we will calculate what is a magnetic flux here through the toroid. In order to do that, we firstly need to calculate our magnetic flux density inside a conductor using Ampere's law. So we will choose our closed contour here. What is the direction of our closed contour? We will choose the same direction as the direction of magnetic field. How do we determine the direction of magnetic field? Well, here we have the direction of current and how this conductor is wounded around, curled around this toroid. So we put our fingers in the direction of, as you can see, our conductor is above our toroid, and our fingers must be in the direction of current, which means that the direction of magnetic field is like this. So it goes in this circle. So this is B, and also this is DL or F. Which means the angle between them is 0. Cosine of 0 is equal to 0 times sum of E. How many currents does our closed contour have? Well, it has one current, 2, 3, and 1 times I. So N1 times I. These are sum of all the currents inside this closed contour. So here we will get B times integral of dl is only L, but L is the length of our circle, which is 2r pi, which is equal to 0 and 1 times I. So B, our B, I wrote it here, inside torus is N1I divided with pi. Okay, this is our magnetic field inside a torus. Now we need to find a flux inside of this torus. So how will we do that? Well, very simple. Okay, this is the center of my torus. Here, where my torus starts, it has rectangular shape. This is its height. Okay. This is the center. So here we will have some ds. On a distance r, which means this infinitely small part is dr. So the same way to calculate it as, so this is integral b ds, where b, the angle between b and ds, well, we have took this surface, this area. So what is the distance, what is the direction of B? Because B goes here, inside we will analyze this part. So at this part it will go from you towards the table. So this is the direction of B. But what is the direction of vector normal? Well, you must look at the directed contour of our conductors, but we have determined the same, we determine it the same way as magnetic field. So here the conductor goes this way, so actually we have this direction of current, which means that this is the direction. This is our this is our toroid, this is our conductor with its current direction, which means the direction of ds is also from you to the table. So this is v times ds times cosine angle between these two, which is 0. Cosine of 0 is 1. So we will get that the flux is equal. Our b is me 0 and 1 times I divided to r pi times ds. Well, what is ds? ds is the base times the height, which is h times base is dr. So what are the borders? Well, the borders are, as you can see, this radius, this toroid starts from A and it ends at B. Not A plus B, but it ends at B. So this is A and this is B. So it goes from A to B. So our integral will be dr divided with r, which is a logarithm. And we will get this. Me 0 and 1, I1. 2 pi h times logarithm v divided with a. So this is the flux through our toroid. In order to find inductivity between these two, we need to find a flux of this coil. But what is the flux of this coil? The flux is the same. B times ds. But now here, what is the case? If we had only one circle, that would be one S, one surface of our loop. And then in that case, F12 would be equal to this flux. But because here we have two loops, that means that this is how many surfaces we have. So our total flux is actually N2 times our flux, which we got, that is it's inside toroid. So we get that it's me 0 and 1 times N2 times I1 divided with 2 pH and B divided with A. So this is the flux on this coil. We need to calculate inductivity, so inductivity is only when we divide this flux with the current. So we will get only without this part. That inductivity is actually this, N equals that. We don't have flux outside toroid. Why? Because if you would calculate a magnetic field here or here using Ampere's law, because of that sum of I, inside you don't have I, outside you would have I in one direction and I in the other direction, so total magnetic flux outside toroid is equal to 0. Because of that, we only needed to calculate a magnetic flux inside toroid, and that flux is equal to the flux of our coil, but only times the circles, how many loops does it have. And that's it. Thank you for watching. See you in the next video.